Welcome to all of you tuning in. We're about ready to start the last session of the day featuring our guest, Michael Moore from EY. A couple of reminders, we'll be sending an email with links to the presentations in the next day or so keep an eye out for that. And we are taking questions at the end of the session, so please don't hesitate to ask a question or two using the questions tab located at the top of your screen. If we don't get to your question, you can send an email to webinar@neo4j.com and we'll get you pointed in the right direction. And lastly, be sure to post about today's connection using hashtag Neo4j or hashtag connections to be entered to win some cool Neo4j swag. Without further delay, I'll hand the floor over to Lance Walter, Chief Marketing Officer at Neo4j, to introduce today's final session.
All right, thanks, Marilee. Well, we hope you've gotten a lot of value out of today's program. And like an Olympic gymnast trying to stick the landing, we're going to try and finish really, really strong featuring Michael Moore from EY. EY has been a close partner of Neo4j's for many years now. They've been sponsoring our events since 2015, and more importantly, teaming up with us to deliver customer success at dozens of joint customers around the globe. EY was among the first to wake up to the transformative potential of graph databases. So it only makes sense that we would tap into a thought leader from EY to share perspectives on the continued evolution of graph technology and how future applications will take advantage of connected data and graphs. Dr. Michael Moore is the National Practice Lead for Enterprise Knowledge Graphs and Artificial Intelligence in EY's Data and Analytics Group. He helps EY clients deploy large-scale knowledge graphs using cutting-edge technologies, real-time architectures, and advanced analytics. Dr. Moore is a very unique talent, and I always look forward to his talks. He's able to speak from direct experience to the C-suites of the world's biggest and best companies about the power and potential of graphs, but he does that rooted in a deep practitioner-level technical understanding of data management technology. Prior to joining EY, Dr. Moore was a general manager for business intelligence at Microsoft, and prior to that, Dr. Moore held a variety of consulting and research roles around data warehousing and advanced analytics. Dr. Moore holds a PhD in integrative biology from the University of California at Berkeley, as well as a bachelor's degree in earth sciences and biology from UC Santa Cruz. Well, let's hear about the future. Welcome, Dr. Moore.
Thank you, Lance. It's great to be here. My name is Michael Moore, and today we're going to be talking about the future of graphs. As Lance mentioned, I lead our national practice in knowledge graphs. And EY is fully in on graphs. We have a really large practice. We have over 200 consultants globally, and we see a really wide range of graph use cases. We've implemented over the last few years dozens of different graphs, and all of them basically are built around the notion of unifying data to extract value out of enterprise data assets. My general prediction, and one of the reasons why I'm so excited about graphs, is that I generally think it's a superior way of managing and interrogating data. And I believe that by the end of this decade, something like 50% of all SQL workloads will be moving into graphs. And I know that's a bold assertion, but the trends are all going in that direction. And so some of the things that are underlying graph adoption include things like just the giant proliferation of data. There's data being produced at phenomenal rates, and that data does need to be analyzed, needs to be connected, and graphs are great structures for being able to do that. Teams have less time to work on data, and so one of the great things about a graph is that the data is already joined, and it has its own semantics and its own sets of connections that are easily interrogated. Cost of memory and compute is dropping, and if you go talk to enterprise data teams, the last thing that they want to see is another data lake that doesn't necessarily add significant incremental value. We also see trends towards federating data. We see this notion of data as a service. We see concerns around DevOps in terms of being able to stand up quickly containerized solutions that are easy to maintain. And then finally, the overall cost of ownership of a large data platform really does need to be balanced by the business value that it's driving. And graphs are really great at creating additional business value from data investments. Neo4j is currently the leader in the graph space. Forrester Wave last year published a really great article looking across a variety of graph vendors. One of the things that's clear, though, is that this is a big market. There is a significant interest in graphs in general, and the main reason is that what graphs allow you to do is connect and rationalize and mobilize your data, and they can do it better than standard tabular data stores. And most organizations now have graph efforts going on somewhere in the organization. That's a pattern that we see a lot. And I think there's a growing realization that if you're a large enterprise and you haven't been looking at graph, you're probably already falling behind the curve. Neo4j, for the first time this year, is in the top 20 of all database engines. And there's a website called dbengines.com that tracks adoption and popularity of different database platforms. And Neo4j, month over month, continues to rise in the ranks and is now considered a completely adoptable enterprise-grade database platform in of itself, and it's the only one with a pure play graph model that exists in the top 20 of all databases currently. At EY, our approach to thinking about enterprise data is premised on a modern architecture that we call a data fabric architecture. And without going into too much detail, the elements of our approach to enterprise data management include things like infrastructure as code, pattern-based ingestion, federated querying across unified data fabrics, analytics workbenches, and then delivering data as a service through a variety of APIs. And so what we're going to focus on in this discussion is what do we mean by a global data plane? And so a global data plane is really an abstracted way of connecting data across multiple different data assets and across multiple different data shapes. There's really two ways that this happens at scale. So one is query federation, and the other is through knowledge graphs. And so query federation is the approach where a SQL query is distributed out across a set of databases. It's usually being passed through some kind of a metadata catalog that allows that query to be shaped for the in sources that it's going to be querying. And then after a couple of minutes, that query returns and brings back a data set. So this is a really useful method for doing things like OLAP queries, and it has the advantage of being able to keep the data in place. It is generally limited to SQL stores, but it's very useful. And so tools like Presto and Dremio are examples of query federation engines. Now, knowledge graphs are a little bit different. So what knowledge graphs do is they're a in-memory repository, and there's usually a combination of data that's been loaded into the graph or metadata that the graph knows about that it can use to access data that's being stored remotely. The main advantage of knowledge graphs, though, is that all of the knowledge graph data is actually kept in memory. And so instead of having minutes to return a query, that query can return in milliseconds. And so knowledge graphs are very useful for unifying data when you're really interested in mobilizing that data so that you can actually do something with it operationally. And so typical use cases are 360 views, looking at end-to-end processes, supply chain, next best action, anywhere where not only do you need to execute a complex multidimensional query, but you need that result to come back very quickly. So I want to focus on a couple of reasons, three actually, why graphs are way better than SQL. And so The first one is that when you use a graph in your data stack, you're pretty much guaranteed a great user experience. The performance of graphs and the complexity of analytics that you can do with a graph far exceeds what you can typically do with a SQL environment. Context is really important. Companies compete on context, understanding the current state of their customer, understanding the current state of product ownership, process, etc. And with graph, you can run analytics that will generate much better context across complex data. And also, one of the things we found to be true at EY is that graphs take a lot less effort to develop. So let's go take a look at some of these. So for the uninitiated, let's start with what is a graph actually. And so graph is a representation of how data is connected. And graphs commonly describe business processes. And a graph database is a database that's optimized to store data in graph format. And one of the great characteristics of a graph database is that you don't have a complex translation between the way the business process was described and the way it's represented. And so graphs have very high fidelity. And so, for example, on the left here, you see a typical e-commerce process where somebody's sending email, trying to get people to go to a website, purchase items. Your graph database would actually have this same design. And you would have, hundreds of thousands, if not millions of email records. Each one of those would have a relationship to a person that it was sent to. You might have web visits where that person visited a website, and you might have product that's in stock and purchasable from that website, and you're looking for purchase transactions of people to product. And so graphs can do a very good job of unifying complex data, and they have high fidelity to the way the business actually thinks about its data. And for that reason, they're very easy to develop, and it's very easy to get feedback on your graph designs from the business, which gives you a lot more confidence in your implementation. So what are some reasons why graphs are great for end users? So one of the first ones is performance. And so here is a comparison of SQL to graph. And one thing that is true about SQL is that you can load data into SQL tables faster than you can load them into graphs. Why is that? It's because a SQL environment doesn't actually build and store any of the relationships that are used to join data. All those relationships are basically inferred. They're represented by primary and foreign keys. And every time a user runs a query, each one of those users pays the cost of doing those joins on the fly, essentially using incremental memory. And that creates with it a whole set of limitations. So one is that the queries run more slowly. Another one is that the queries can't be too complicated. And so this is one of the main advantages of graph over SQL. So graph, instead of the end users paying that cost, the cost of building relationships is paid one time as you load data. And then since essentially the end users are querying a pre-joined data fabric, there's no additional cost associated with joining data. And because you've also computed all logical possible relationships as the graph has been built, right out of the box, you get the ability to execute much more complicated queries. And this is one of the main analytical lifts associated with graphs. Graphs are also good at creating better context around data. And so this process of creating persistent relationships really pays off in a bunch of ways. Now, so for example, if you have wide data, which means that I have lots of different entities that I need to query in a single query, I can do that with a graph. And I can unify all those data, and as Customer 360 is a good example of this. If my data is complicated, say I have many to many relationships where my individual records have many associations with each other, graphs are very good at doing this. These kinds of structures are really difficult to represent in SQL. In tabular format, you have to have things called join tables, and there's quite a lot of overhead with building and maintaining those kinds of structures in SQL. But in graphs, you can model it directly, and you can very easily traverse these kinds of complex structures. Another area that SQL has difficulty in is in deep data. And so deep data, basically, you see that in essentially two forms. You see data that has recursive relationships. So you think of genealogies, parentage, things like that, where in order to execute that query, you'd have to take a large deep table and join it against itself many times. Another one is deep hierarchies, where you've got a business process that has many parent-child relationships stepping down through multiple levels of hierarchy. And we've done projects on say SAP data that might have 10, 12, 15 levels of hierarchy in it. Very difficult to interrogate all that data at once. In a graph, you can model it directly and interrogate it directly. Legacy data is very common in the kind of engagements that we work on. It's not unusual for enterprises to have grown through acquisition, and so we often see data problems around siloed data. And graphs are really great at being able to essentially bring together data silos, even if there isn't a broader initiative to, say, rationalize that on its own. Because you can basically bring in data from individual data stores and then use the graph to break down those silos, map that data, and unify it. A similar problem that we see is frozen data. And by this, I mean this is data that's been loaded into a data lake, but perhaps because of how voluminous it is, or maybe because there hasn't been a ton of effort conforming that data, you effectively end up with siloed data even inside your data lake. And so graphs are very good at mobilizing data that is maybe not adequately conformed and joined or modeled, even in the data lake. And so you can do extracts of individual fact tables, bring those up into a graph, and map them. And then finally, one of the real values of graph is analytically their ability to do inference. And so this is what I call hidden data. And one of the very common underlying drivers of use cases around graph is if you put a lot of data into a graph, you can then actually begin to interrogate the topology of the graph and find things out that aren't widely known. And this is the process of inference. And so in this example, if I've loaded some data into a graph and I know that A is connected to X and B is connected to X, then I can infer there must be some kind of a relationship between A and B. And so maybe these are two consumers who have the same product interests, or maybe these are two synthetic identities that are part of a fraud ring. So graphs are very good for determining relationships and that may not explicitly exist. And this is a really common kind of use case for an operationalized graph. So either doing things like recommendation engines or doing fraud detection. In general, and particularly with Neo4j, I feel that graphs require less effort to develop. Most of our work is able to be done relatively quickly when we choose to deploy a data fabric that's based on a graph. And some of the things that we find that we can leverage is the notion that all of your data is in memory. Right out of the gate gives you a ton of performance. Cypher is a very expressive language for writing very fast, complex queries. When your graph is modeled correctly, you end up with a structure that has really clean and elegant semantics, that has high fidelity to your business processes. And then typically, you'll start with one use case, solve that use case, and then very quickly, your graph will start to support other use cases that other stakeholders are bringing. And it's not unusual for a graph to be a combination of both OLTP, transactional processing scenarios, as well as analytical scenarios. We like the enterprise database features that currently ship with Neo4j. There's great features around security, scalability, and containerization. We'll touch on a couple of these. And then also it's important that there's good language support and good API support, and Neo4j provides both of those. There's dozens of languages that you can use to integrate with your Neo4j graph, and we do a ton of work with GraphQL. We really find that is a massive accelerator for building full stack applications. The other thing that is great about Neo4j is that it gives us a lot of latitude in how we want to do deployments. So we can deploy on-prem onto physical hardware. We can deploy into cloud platforms, and Neo4j has also just recently released Graph as a Service with its Aura product, which we expect will drive a lot more use and adoption of Graph. And then finally, there's just a lot of tooling, visualizations, data science add-ons. The community around Neo4j is really large. It's easy to solve problems. And I find that overall the platform is very easy for any technically competent IT team to adopt. And so, all of these features really help contribute to lowering the amount of effort that it takes to deliver business value using a graph platform. So let's pivot a little bit and talk about how we actually approach the problem of data unification. So the way that I think about it is that there's essentially two general approaches. You're either ingesting data or you're doing some form of federation. And so with a graph platform like Neo4j, data can come in at different velocities. And so, for example, you can have an application that's executing real-time transactions through APIs. You can be consuming message data. You might be running batches of either structured data. You might be running batches against things like ontologies or business process descriptions, things like that help you actually build out the knowledge graph with consistent semantics. And you can do things like even ingest, pointers to blob stores, where you definitely want to keep that data where it exists. Maybe it's imagery, maybe it's something like, something else. But you do want to know where it is, and so you want the metadata so you can make that data discoverable. On the federation side, Neo4j, for example, enables queries out to graph shards, so you can have multiple independent graphs that are logically linked. You can query out to other structured data sources like SQL. It has JDBC connectors, so you can execute a query from Neo4j and hit an Oracle database, or you can process, or you can do that through various transactional APIs. And then finally, you can also federate queries down to other types of data stores. So if you have a polyglot architecture, you can actually query things like document stores and other forms of databases. So it's pretty flexible in that sense. And all of these features contribute to building an integrated data plane. In general, as we approach a graph problem, we generally go through this process of identifying what we consider to be a graphy problem. And so a graphy problem would be any problem where the data has any of those characteristics that I previously ran through around data complexity. You generally build some kind of a quick POC to test the analytics and the overall concept of the graph. Those will often migrate into a cloud pilot, which will then evolve into a production build. And generally speaking, it doesn't take a very large team to build a graph. Usually there's only a handful of roles, architect, a couple of data engineers, maybe a full stack developer or two, or a data scientist, depending on the application, or a report developer. And so this is a process that we tend to repeat over and over again with our clients. And the main thing that we're trying to do is, elicit what is the difficult problem that the graph is going to solve, and then be able to deliver in a reasonable time frame innovative new solutions that show how the graph can augment their existing data infrastructure. And so if you were to take a quick step back and you were to unpack a lot of our enterprise knowledge graphs, you would see various characteristics in those graphs represented this way. So generally speaking, we'll have done a lot of work around data unification. There will be attention to creating understandable, business-friendly semantics, which means how we name fields and nodes and things like that. Oftentimes, there might be some structured ontologies or taxonomies that need to be imported for various reasons, maybe compliance or industry standards. Not all the data needs to be in the graph. So we might have pointers out to where data assets are actually held. Graphs are often used to just simply discover data. What data do we actually have now that we all have it in one place? Data lineage is an important characteristic that is easily handled in graphs. And so we can actually trace the metadata or how data changes or the various handoffs associated with data processing. And then finally, we'll usually have some elements around graph analytics. And so these might be advanced algorithms that we're running, or maybe different kinds of frameworks and analytical harnesses that we've built, either in Cypher or Python or something like that. All of these things contribute to an enterprise knowledge graph that allows the business to ask and answer new kinds of questions and generate new insights that were previously locked up. Okay, so let's take a quick run through some example graph schemas. And so this is like that prior example that I showed you, but these are a little bit more built out. So each one of these circles represents a node. Those can be hundreds or millions of records, depending on what the nature of that data. But in a typical customer 360, the idea here is that I'm looking across the entire enterprise landscape, and I'm unifying a variety of transactions. And out of that, I understand things like project ownership. I understand aspects of the customer's identity, and I understand where we're actually seeing that customer in terms of the kinds of interactions and channels that customer is appearing in. Here's another example of how we can use graphs to do things like master data management, for example. And so in this scenario, perhaps this is a B2B customer, and the customer has contacts. And what we're interested in is understanding the quality of those contacts. This is a very common problem in B2B selling and also marketing. And so if I look at any one of these individual contacts, I might explode their core data elements, so things like a phone number or an email. And because I can use the graph to trace data lineage, I can actually know the source and keep track of the source of each one of those core data elements. And then depending on how authoritative I feel those sources are, so maybe a physical address coming off of a billing statement, or maybe an email address coming off the last time I saw them on a web form, or a phone number that was validated during a telesales drive, right? Each one of those individual core data elements can be ranked in terms of their legitimacy and accuracy. And I can use this graph to essentially reconstruct a golden record for this customer contact on the fly. And this is a very common scenario, and graphs solve this very well. Here's another type of approach. And so this is more in the realm of what we would call an asset 360. So the centerpiece of this style of graph is all of the information that might be associated with, say, a major asset or a major investment. In this case, this is an energy sector example, and the core asset here is a well in an oil field. And so the kind of data that is associated with this is very voluminous. It's a combination of structured data, it's a document data, and a ton of unstructured data. And using a graph, we could basically make all of this data discoverable. We could load the structured data into the graph, and then we can have integrations that can pull data from document stores. And so I can keep the metadata for my semi-structured data in the graph, but if I need the full document, I can go reach into those document stores and grab that. And then I can also keep all of the metadata for the largest volume of data, in this case, which is all my unstructured data. So you think imagery, you think logs, things like that, a lot of scientific data, technical data that's probably not appropriate to pull into the graph just in terms of the shape of that data. But with the graph, I can make all of that data discoverable and searchable, and I can drive queries that can produce that in whatever the user context is. And so, for example, here is a graph query that is federating to Couchbase. And it hits Couchbase's full text search endpoint, goes and searches for some documents, and then pulls those documents back directly into the graph. And so this is a really good example of how you can do query federation right out of Neo4j into other types of data stores. Here's another example where if I have the metadata for unstructured data, in this case, this is some imagery, subsurface imagery. Maybe I'm holding this in a blob store, but I have the metadata for this image. And so then my graph query then basically returns the URI for this image. And then that can be flowed all the way through to an end user application. User clicks on that link and is able to access this image. So very useful. When it comes to loading structured data into Neo4j, Neo4j offers a transactional endpoint, offers JDBC connectivity. And here, this is just a quick screenshot of a tool called StreamSets that we often use for ELT processes. And here we're able to load 1 million records into Neo4j across 5 parallel threads using Neo4j's transactional endpoint that allows you to execute commits on the fly. So very good performance in terms of just standard batch loading. If we wanted to step into more real-time data, Neo4j has a Streams plugin that allows Neo4j to function either as a consumer or as a producer of messages. And so here's an example where now I'm using StreamSets to fire off messages into Kafka, and then Neo4j is consuming those messages. And in this example, we're able to pass, again, about 1 million messages in 30 seconds into Neo4j from a Kafka broker. Similarly, Neo4j itself can function as an event producer. This is very useful for things like change data capture. And there's a screenshot of what these configurations look like inside Neo4j. But basically, every time there's a change in the graph, Neo4j can post a change data capture message out to a Kafka topic. And that can be used to monitor changes in the graph or used to sync with other downstream data sources. So these are all very useful types of capabilities that enable Neo4j to actually sit in that data plane and work with real-time data. So let's talk a little bit about semantics and data lineage. One of the things that we use graphs a lot for is understanding data lineage. And this is a generic schema for how you might think about lineage and source mapping for different data points in a large enterprise data landscape. And so here, this is essentially a view that's anchored on an individual field or a property. You can see that in the middle of the schema. And we keep track of where this field came from. So what was the source of this data? What was the table that this data came from? What was the system that table was pulled from? Whether or not this particular property in the graph was derived from some other property, and then whether or not this property has some mapping that might be used by some downstream system that requires an additional transformation in the way that property is named. So perhaps like a canonical mapping model, or maybe there is there's a downstream execution system, like say a Pega system that requires fields be named in a certain way, or an API that requires fields be named in a certain way. And so you can keep track of all of those aspects of a single data entity in a graph, and then be able to very quickly determine whether or not you're in compliance, or you're conforming to the overall semantics of the graph. And you can also determine very quickly where a particular data field came from and what changes have been performed on it. It's not uncommon for us to also have to work with structured ontologies and taxonomies as we build out the semantics of our knowledge graph. And Neo4j has a great facility for importing RDF ontologies. And so here, for example, this is a clinical measurement ontology that's been imported into Neo4j using the Neo Semantics plugin. And this allows you to basically bring in large volumes of structured RDF ontologies, bring those directly into the graph. And in my opinion, they actually become much more useful because now I can align those ontologies with actual operational transactions. And so the ontology and all of its descriptive power is actually coupled with real-time operations that the business is performing. And so that, to me, that's a great marriage. And let's finish up on some aspects of Neo4j scaling. One of the real advantages of Neo4j is that there's been a lot of attention to different styles of scaling that are very helpful in rapidly putting together a graph-based solution. And so one of the first things that we like a lot is the fact that you can actually run multiple graphs on the same Neo4j server. And so it's not unusual for us to have a semantic graph, a development graph, maybe a UAC graph, all running on the same server. This is efficient for development, and it's also efficient for licensing. On the production side, Neo4j allows a really high degree of scalability in its approach to clustering. And so the Neo4j clustering philosophy is organized around a set of core servers that are executing reads and writes, and up to 150 or so read replicas. And so, and you can you get automatic load balancing through Neo4j's Bolt protocol, and it can discern whether or not a query is a read query or a mutation query. And if it's a read query, it can route that query to any one of the available read replicas, where if it's a mutation query, it'll route that query to one of the core servers. And it'll also put a bookmark on that query so that an end user can immediately read any updated data from the server that that data was just written to. And so this gives a good combination of high availability and failover and operational scalability for large large enterprise deployments. Another aspect of scaling is Neo4j recently released what it calls its Fabric capability. And so Fabric is the ability to shard graphs across multiple graph instances that are still logically related. And so this allows you to do query federation across different instances of Neo4j graphs. And this is a really powerful capability that is only really just now being leveraged. But the implications of graph sharding that Neo4j Fabric enables is effectively that there's now no upper limit to graph size, because you can have shards of different data domains, and all of those shards can be logically linked on demand. And so here's an example, just a very quick and dirty example using the movie graph. So here we have two shards. The first shard is a shard of movies and actors, and the second shard is a shard of movies and non-actors. So think directors and producers, etc. And so these are two separate graphs, each running on its own instance. And with Neo4j Fabric, I can run a federated query from the from what's known as the Fabric graph launching point, and I can actually reassemble data across both of these shards. And so here you can see in this federated query result, we're actually returning the composite of both the actors and the non-actors that were involved in the matrix. And so you can imagine how this could be leveraged at scale with, say, data from different divisions or different domains, and be able to basically service, operational data stores, but then also be able to execute enterprise-wide queries. So this is a really, really great feature. Okay. So finally, just to finish up, the way that we look at graphs is, we find them to be very fast and efficient. We think that the model is super intuitive. There's great interoperability. They're transformative. And finally, they're very strategic. And they are an excellent augmentation to any kind of ongoing data management strategy. Particularly if there's already been quite a lot of work done on things like building data lakes, and now the effort is pivoting towards trying to mobilize that data and getting it into the hands of the business where it can be used for decision support. And so we feel that graphs can add value in any environment where data is interconnected and relationships matter, where data needs to be read and queried with optimal performance, and also where the data is evolving and the data model is not always fixed and needs to be iterated and shifted much more flexibly. And with that, I'll say thank you, and I can address any questions.
Great. Thank you so much, Michael. That was an excellent presentation. It was so informative, and we've had a ton of questions. So I want to remind the audience, if you do have a question to submit, you can do that in the questions tab located at the top of your screen. We are running a little tight on time, so if we don't get to your question in this Q&A format, we will get back to you, or you can send an email to webinar@neo4j.com. But let's go with some of these questions that we have. So here's one that says, in one of your slides, you said that you feel that graphs require less effort to develop. So how long does it really take to develop one?
We can usually do a robust POC in about, anywhere from like, 14 to 16 weeks, using, say, a snapshot of data.
Oh, excellent.
Yep.
And following kind of on to that, so here's a question that asks, can you start in just one area, or do you have to do everything at once?
Yeah, we actually recommend that that our clients start, with maybe just one use case and a relatively simple data landscape, because you can always add more to your graph. It's very simple to add additional data to a graph at any later point. And so we often see customers beginning with a single use case, and then once they understand what they can do with the graph, they'll typically then expand into other use cases.
Okay, great, thank you. And then here's one that asks, how large are the graphs that you typically deploy?
So we generally build pretty big graphs. It's not unusual for our graphs to be in the billions of nodes, terabytes in size.
That's pretty big. So let's see, here's another one. Oh, and this kind of goes along, if these are related. So when you talk about performance, how fast are graphs really?
So graphs are very, very fast, particularly for doing things like executing singleton queries, where say I'm maybe passing in a customer ID and I want to interrogate 20 or 30 entities around that customer. That's a very common use case. We would typically see response times of around 50 to 100 milliseconds in a full stack application.
Okay, and then let's have one more before we wrap up. How do you manage the organizational change that the graph enables for the business?
It usually takes some discussion. We try to encourage a give to get model. We try to help our clients who are going down the graph path to think about establishing a graph center of excellence. And it often does require a fair amount of negotiation to get different parts of the business to contribute their data to the graph. One of the nice things about the graph is that if they contribute their data to the graph, we can usually provide value around that data back to that business in short order. So this is not like a 5 to 7 year data lake build or something like that. So you're talking months to value instead of years.
Oh, that's excellent. Thank you. And it does look like we're just about at time. So Michael, I want to thank you again for your time today. It was a pleasure having you with us.
Thank you. It was a pleasure.
Excellent. And then I just want to let our audience know that our next connections will be in March. So we hope to see you there. Thank you for spending your time with us today, and make it a great day. Thanks so much.